Okay.
Okay. Yeah. Welcome back, everyone, for the third session, the last session for today. This session will be handled by Dr. Biswabandan Panda from IIT Bombay. He
I
prefers to
think
be
you
called
have
as
already
Biswa.
introduced Kalyan, so I don't think
Yeah,
it's
I'll just
necessary.
add one more thing. So he prefers to be called as Biswa. So feel free to call him that. And usually his lectures are filled with a lot of anecdotes and wiki points from our day-to-day life. So I'm looking forward for such points from him. Over to you.
Okay, thanks. Thanks, Kalyan, and nice to see you after a long time, although through Google Meet. Yeah, so before we start, I just want to thanks, the organizers for this initiative and putting up this faculty development program. It's kind of an interesting topic, and ideally we would like to have an ecosystem where more and more folks are actually aware of the issues related to system security or hardware security, right? So kudos to the team. Before you wrap up the FDP, maybe on day 5, don't forget to clap for the organizers. Okay. Before I jump in, maybe few protocol, especially because you are dealing with this online setup. So you feel free to put up your questions on the chat box. What I will do is I have created multiple breakpoints. So whenever we pause or break, I will take all the questions and then answer. So this way we will be able to take maximum number of questions in one go, and there will be minimum interruptions, mostly because of the internet issues or bandwidth issues, right? Feel free to ask more and more questions. It's perfectly fine if I don't cover all the slides. The goal is to build some curiosity, right? And as I have already mentioned, so I have to speak for 7,200 seconds. It feels like eternity, because I kind of work in the area of microarchitecture where 7 nanoseconds is 2 months. Okay. And then last but not the least, this is just one of the sessions, but feel free to email or ask your queries even after the session or after this FDP. Okay. So that, let me get started. So I'll be talking about microarchitectural aspects of security. Some of the high-level overview was already given by Neeraj. So what I would do is I'll also take a 10,000 feet view instead of jumping into the subtle nuances. So when someone says architecture or computer architecture, right, the first thing that comes to our mind is, there is some assembly language programmer, maybe there is an ISA, x86, RISC-V, whatever, and then some registers to operate on, right? So that's the overview of architecture, right? And this interface is actually visible to the programmer. As a programmer, you can actually write assembly language programs which can do the job for you, depending on your requirement. But what I'll be talking about is microarchitecture, which is not exposed to the programmer. They are hardware structures which are there inside our chip to make our job easier, or to make our programs run faster, for example, right? So in this session, what I will do is I will mostly talk about some of the microarchitectural units, for example, caches, beta branch predictors, and out of order execution that is kind of a base for any modern processor that you will see in today's world. And then we will jump into the security aspect. So the first half an hour or maybe 30 minutes will be just understanding this microarchitecture. Once we have an understanding, then we'll jump into the security. Okay. So let's start with microarchitecture 101, and then the moment someone says microarchitecture, caches come into picture. So this is like the king of microarchitecture, right? So if you are, if you have already taken a course on architecture, if you know about caches, it's good. If not, it's even better, right? You'll learn something new. So let's have a pretty idealistic, system where you have a processor, which I'll be calling as a core, and then there is a memory. So Neeraj has already talked about the notion of processor, memory, OS, and all. Here, what I'm showing is processor will actually run programs and then execute instructions, but the data and code will actually come from the memory. Okay, and then as you must be knowing, memory is actually off chip. It's not part of the processor. So to get the data from the memory, the processor has to send an address. So let's take a simple example of 32-bit address, and the DRAM will respond to data, but it will take hundreds of cycles, right? And this is kind of a bottleneck in modern system. It's kind of an old problem, nothing new. But even if we have so many sophisticated ideas in the systems and architecture world, we are still bottlenecked by accessing data from memory. Okay. So the goal here at the moment is to minimize the number of DRAM accesses because they're kind of costly. Okay. So to understand the notion of bottleneck, the bottleneck is actually in the form of latency or bandwidth. So when I say something is creating a bottleneck, in the form of latency, it may happen that the code is demanding for the data at time t, but the DRAM is responding data at least time t plus 200, right? So that's the latency. Bandwidth is actually the rate at which the DRAM is actually responding or pumping data back to the processor. Okay, so this is more the better. Okay, latency lower the better, bandwidth higher the better. Okay. But if you look at the industry trend, and if you are following the latest DRAM standard or the DDR standards, you'll find that bandwidth problems are kind of, it's not a big problem. For every generation, the bandwidth is kind of getting increased, so it's kind of good for the programmers. But the harder problem is the latency problem. And then there's a famous quote which says that latency problems are harder because you can't fudge the speed of light, right? And then obviously you can't write God to make your latency minimal. So that's the context I want to bring in before jumping into the caches or the other microarchitectures. Okay, so this is the problem. This is the primary problem. Why it happens? Okay, so conventionally, all the modern processors are actually designed by following what is called a von Neumann architecture. So the base of von Neumann architecture is the data and the code is stored in memory. And whenever a processor demands or processor needs something, it will actually ask for the data and code from the memory. Okay. But as I already mentioned, this is actually not part of the process. This is off chip. So this takes hundreds of cycles. And in computer architecture, this is termed as a memory wall, because there is actually a big gap between getting the data from processor from the memory into the processor. So this is literally termed as the grandmother of all the architectural worlds, and then this problem is still open problem in today's world. Like, how can you bridge the gap between processor and memory? So simple answer: cache it. Okay, and then before jumping into what exactly is a cache, why it works the way it works, you can assume one more hardware structure here, which kind of stores subset of data that is already present in memory. Okay, we'll decide which subset of data, but to start with, let's assume if the DRAM is a 4 GB, we have stored something here, which is less than 4 GB, of course. Okay, and then now if the processor demands for data by sending an address, it will get a faster response compared to the 200, 300 cycles. Okay. But why this works, or why exactly caching is used widely, not only in the field of architecture, but overall in computer systems, you will find caching is a common concept. Well, the primary reason for caching is a term called locality. So let's understand what exactly locality is. So this slide is showing a plot where the x-axis is showing the notion of time, okay? And y-axis is showing the memory addresses. So whatever the processor is requesting for, okay? So if you closely observe this particular behavior in terms of memory access patterns, you will find a particular address is getting referenced or re-referenced multiple times, okay? And that is known as the temporal locality. Same address is getting accessed or re-accessed by the processor again and again. You can also find something in the form of spatial locality, where whenever you access some address, you also access some of the adjacent addresses. For example, if you are accessing address 21, you can see that address 22, 23, 24 kind of are also accessed, right? So based on these two simple and intuitive principles, what you can do is you can actually cache the data based on locality, right? And that's why the definition that I had in the previous slide, it's actually a speculation technique. Okay, so this is kind of a unique definition that I'm putting in compared to the textbook definition that you may find. Why it's speculation? Because you are speculating that the program has locality, and because the program has locality, I'm putting a cache so that you will get your data from the cache. Okay, so few examples that you can correlate from your programs, right? So if you are accessing instructions, you will find this kind of access patterns, and then if it is going through a loop, you will find the same access pattern again and again. Stack accesses, try to correlate with your function calls. You enter into function, do something, come back from the function, right? And then many more such accesses. For example, a simple array or a 2D array accesses, which can show you the utility of temporal or spatial locality, right? So now that we know that caches are useful, and we should have them so that the memory wall problem will be solved. Ideally, we should have a cache which is which can be accessed in few cycles, or ideally maybe one cycle. That means the latency should be low and the capacity should be high. So these are like two extremes, right? But in reality, these are the trade-offs. You won't get a high capacity cache that can provide low latency. They are kind of contradictory or conflicting trade-offs, right? So instead, what you need to have is maybe a bunch of caches, and then create a notion of hierarchy that I will talk about in the next few slides, and try to bridge the gap of memory wall. Okay. So at this moment, some of the questions that should come to your mind is what should be the size of the cache, whether it should be implemented as registers, SRAM array, DRAM array, blah blah blah. I won't go into the details or the answers of these questions, but think through it. The way I would like to ask this question is from a processor point of view, right? So why exactly we build up this notion of cache hierarchy? So let's ask this question to the processor. Okay. So this is again a 1,000-feet view of a modern processor that you will find in the modern laptops, right? So here I am showing a few instructions. Let's say instruction 1, 2, 3, 4, 5. And they are getting fetched every cycle. Okay, so loads are nothing but memory accesses. That means the processor wants to load something from the data. The other instructions are simple arithmetic instructions for which there is no need to go to the memory. Okay. Now, what modern processors do is they actually execute these instructions out of order. That's what the O3 stands for, out of order, which means if there is no dependency among these instructions, all these instructions can be executed out of order. Right. For example, this subtraction operation can actually finish before the load gets over. Right. That's the base for out of order execution. But finally, the program should have a commit point, and that should be in order. The way the instructions enter the processor, they should also leave in the same order. And that's actually creating a bottleneck, because if the first instruction is taking, let's say, 300 cycles, it's going to memory, even if the other instructions are done before time, all the other instructions have to wait for the first instruction to get completed. Okay. So ideally what we want is that all these loads should take maybe 1 to 10 cycles or something pretty minimal, so that the process should not be bottlenecked for the data. Okay. Just to re-emphasize the impact, let's put some numbers. You can go through it again maybe later. So I'm talking about a modern, pretty aggressive processor, which is 4 fetch, 4 issue. So the meaning of 4 fetch is in one cycle you are fetching 4 instructions. Okay. Let's assume the frequency of the processor is 4 gigahertz, which means the cycle time will be 0.25 nanosecond. So every cycle, the processor is fetching 4 instructions. Okay. Now, if we consider DRAM access time of 100 nanoseconds, so you can easily correlate with number of instructions that can be executed for handling one DRAM access, right? So if one cycle time is 0.25 nanoseconds, in one cycle you are fetching 4 instructions. That means you can fetch 16 instructions per nanosecond. Okay, in 1 nanosecond you can fetch 16 instructions. And if we kind of bottleneck by one DRAM access, which is taking let's say 100 nanoseconds, that means the processor is waiting for that DRAM access to get done, and ideally the processor should have executed 1600 instructions. Okay, this is just a theoretical example. Real processor won't wait for 400 nanoseconds, assuming it can execute 1600 instructions. There is an upper limit, but just to emphasize the impact of this DRAM latency, this is a hypothetical example. Okay, so now if we have caches, and ideally, as I mentioned, the caches should have few cycles of access latency, and that's only possible if you have a small cache. You can't have a bigger, larger cache with small access latency, right? So for that, what you should have is a multi-level cache hierarchy, where you kind of start with few KBs, and then maybe hundreds of KBs, and then maybe thousands of KBs. And as we go away from the processor, the capacity grows up, and also the latency goes up. So the obvious question that comes to our mind is, like, how many cache levels do we design, right? 1, 2, 3, so which is named as L1, L2, L3. Well, you can do it, you can put multiple levels as long as the total latency for getting the data is actually less than the DRAM latency. Because the moment you get a access latency which is same or similar to DRAM, there is no point adding a cache. It is better to go to DRAM instead. Okay, so I'm talking about all these things because this will create a base for our security part that we'll discuss after maybe half an hour or so. Why this latency, the latency differences can be, used as a tool for leaking information. So far we discussed about the notion of multiple cache hierarchy, and there are typical 3 levels of cache like L1, L2, L3. So L1 is usually designed for latency and bandwidth, L2 is designed for latency, and L3 is designed for capacity. Okay, so these are the design parameters that microarchitects keep in mind before designing a new cache hierarchy or a new cache design. Okay, so I will pause here, and I would like to take questions now. So if there are any queries so far, we can take it now. So if there are no questions, we can move on. Is this everything clear so far? Maybe a thumbs up or something that may help me. Okay, so this lecture won't be about the core part. The high-level overview that I have provided is the processor core is kind of out-of-order processor, which is kind of executing instruction in an out-of-order way, but it is still bottlenecked by the DRAM accesses, because finally you have to complete the instructions in the program order so that the programmer visibility or the programmer view should be respected. Okay. Okay, there are questions on organization of RAM and ROM, but again, that's not under the purview of this session. So maybe I will delay it for the other speakers when they talk about DRAM. Maybe that is the best time to answer. Okay, more questions? Okay, so if there are no further questions, so we can move on. So at this moment, we have just discussed about the notion of multi-level cache hierarchy. Okay, good. So now that we know that caches are useful and caches can actually hide latency, which is a good thing for as a programmer, it's a good thing for systems, it's a good thing. We should also understand how exactly we can access the contents of a cache. Right. So far we have just looked at cache as a black box, right? So the way I would explain this particular event of interest is you assume that cache is nothing but a collection of bytes, okay, where byte is the atomic unit of information, okay? So this slide, you can see that there are like boxes, and then each box is kind of 1 byte. And then the collection of bytes is actually known as a block or a line. Typically in the modern processor, you will find block size or line size of 64 to 128 bytes. Okay. And then what happens whenever the processor send a request? So let's assume 32-bit address. Let's not get into virtual address or anything. Let's just assume that there is some address which is sent by the processor, and it's a 32-bit. Now I want to find out where exactly my data is, right? So you can easily correlate this with your indexing mechanism that is already there in your textbooks, right? So whenever you want to search for a particular concept, you go to the index part and then search for that particular keyword and then go to the particular page number, right? So same thing happens here. You take the address, and from that address you actually try to find out which line number the data is actually present, or the line number of interest. Okay. So in this slide, I'm showing a cache with 1024 lines. That means you need 10 bits to identify one of these 1024 lines. Okay. So once you know the line number, next thing will be which particular byte, because line or the block is a collection of bytes. If you want to extract few bytes and not the entire 32 byte, then the other or the next 5 bits from your address can help you finding out a particular byte. Okay. So this is the first step of getting the data from the cache. There are other things that I will get into it story. So let's assume this is the 32-bit address, and we have 1024 lines. So we extracted 10 bits for index, lower 5 bits for the byte. That's because we have a 32 byte cache block. Rest of the bits are used as tag. Okay. So the way it works is the cache controller will actually extract the index bits, and it will actually try to find out the line number. Once it finds the line number, it actually compare the tag. Why? Because we are not storing data for the entire data. We are just storing a subset of data. And it may happen that the upper bits may be different, even if the lower bits are the same, right? That's why it's extremely important to make sure that you are actually getting the data which is requested for the same address or the address of interest, right? So you go to the index, compare the tag, and then finally get the data, right? So this is how it will work. So you have this address which is coming from the processor. You kind of partition it into multiple chunks of tag, index, and byte offset. And once you get the line number, you compare the tag. If the tag provides a hit, you extract the data. Okay. So that's how this particular cache works. So the organization that I have just discussed is known as direct mapped cache, because there is a one-to-one mapping between index and the location from which the data can be extracted. Okay. So for a given index, you can actually go to a single line. Okay, this is the direct map cache. But it has its own limitations, but let's not get into that. This is not a lecture on architecture. What you will see in modern processors across all the cache level is something called a set associative cache, where I'm bringing another level of hierarchy. Right, first we started with the notion of bytes. Collection of bytes is actually a line. And now I'm saying collection of lines is actually one set, right? So now I can say that one set is collection of, let's say, 2 lines. So that will be termed as a two-way associative cache. Okay. So now the process remains similar, if not the same. Once you get the address from the processor, you extract the index bits. But now index will tell you the set number, not the line number. Because now we are no longer operating at the granularity of lines. Once we get the set number, now we have to compare the tag for both the lines, and whichever line gives a hit for the tag, we will extract the data. So let's see that, how it happens. So we get the index bit. Based on that, we'll actually compare the tag for both the lines, because it's a two-way associative cache. And whichever line provides a hit, you'll actually extract the data from that particular line. Okay. So again, this is extremely crucial for the security part. So please keep in mind that there is something called associative cache, and it's a K-way associative cache. Okay, the K can be 2, 4, 8, 16. So you can again go through this slide later just to understand or appreciate how exactly a 4-way associative cache will look like. Okay. A bit different way to understand the entire caching or the indexing mechanism is if you are like for follower of Sherlock Holmes, right? So the cache index is nothing but the street address, right? And the tag bits are nothing but the famous number 221B. And finally, you want to meet Sherlock Holmes, so that will be a byte offset, right? So hopefully it helps to correlate the actual caching or indexing mechanism. By the way, one thing that I should mention here, though we are discussing about the cache hierarchy in the form of memory, caching can be used in any form. For example, Neeraj was talking about TLBs. There are branch target buffers. Anywhere you want to store a subset of data based on locality, that can be termed as a cache. Okay. And finally, you can also design an extreme cache where there is no notion of fixed associativity, so which is known as a fully associative cache, where a particular address can be present anywhere in the cache, right? So that's why there is no index bits here. What you need to do is, whenever you get an address from the processor, you have to compare the tag of all the lines. So it is super costly. It's not implemented in any modern processors. But I will come to this again during the security part and how this can actually help providing security. Okay. Okay, then. So in summary, what we discussed so far is given an address from the processor, the cache controller divides into chunks of tag, index, and offset depending on the size of the cache, depending on the number of lines, depending on the associativity. And finally, it will extract the data and respond back to the processor, right? So the two extremes that we can have is a direct mapped cache, where there's a one-to-one mapping between index and the cache line, or a fully associative cache where the data can be present anywhere in the cache, right? And it has its own pros and cons. We won't go into those things, but we'll just keep in mind that these are the common cache organizations. Okay, pause again. Any questions? So I'm looking at the chat window through my phone. So if you have any questions so far, anything related to the cache hierarchy or the indexing mechanism? If not, then we can move on. Okay. So I'm assuming this was kind of easy, maybe. So it's kind of easy to follow. So let's move on then. Okay. So now that we have understood the notion of caches and cache hierarchy, let's look into the entire processor and memory together, right? So we started with the notion of processor interacting with the memory. And then we said, okay, memory is kind of costly, so let's have multiple caches in the form of L1, L2, L3, which is also known as LLC. But then you will find that there are different caches for data and code. So code is actually needed when you want to load your program. First, when it's loaded, you need to get the code, and then the processor will start executing the instructions, right? So you will find that there's an instruction cache, and then there's a data cache, but after the L1 level, you will find that all the caches are kind of unified. They store both data and instructions. Okay. So at a high level, the interaction between processor and the L1I is actually termed as the front end of the processor, whereas the interaction with the L1D and anything related to data is actually known as the back end of the processor. Okay. So let's look at the overall interaction. How does it happen? We have already understood the notion of indexing and how exactly the cache controller can provide the data. Now let's look at a particular address, let's say X, which is sent by the processor. If it gets a hit, that means the data is present in the cache. you respond the data in few cycles. If not, you kind of wait for the DRAM to respond. Okay. So there are many microarchitectural techniques that I'm not showing here, but modern cache controllers can actually handle multiple misses. In this example, I'm not showing that, but you can actually handle multiple misses while handling some of the other requests which is coming from the processor. Okay. So the misses can be of various kinds. This is again a pretty high-level overview of the classification in terms of misses. So if you're accessing something for the first time, you'll get a miss, which is a compulsory or cold miss. And if there are two different addresses which are mapped to the same index, for example, same set, then it will create a conflict miss, and it may happen that the data is not present because of the conflicts, right? And finally, as the cache size is kind of limited, it is not like it's in GBs or TBs. So capacity is also one of the concerns where you may get misses at various levels of caches, right? So on a miss, what exactly happens is there is a term called replacement policy, which is responsible for deciding which particular block to replace or evict. Okay. So a simple example will be a Lru policy, which I guess most of you will be familiar, right? So for a given set, if the set associativity is, let's say, 8, right? So there are 8 lines in the set. The eviction policy will decide on a miss which particular block to evict or replace, so that it will provide space for the new incoming block, right? And when the new block comes, the LRU policy actually inserts the new block in the MRU position and then shift all the blocks one step towards LRU, right? And the other sub policy is known as the promotion policy, which deals with while you are on cache, if a particular cache line gets a hit, whether you should promote it to some new place or you can just leave it. So in the simple LRU policy, you will find that whenever you get a hit, the block is promoted to MRU. Okay. So all these policies that I talked about, they're kind of textbook kind of policies. In real world, LRU is kind of not used for multi-core systems. There is a variant called RRIP-based policy, which are commercially implemented, some avatar of RRIP. Again, that's not important. What is important is the replacement policy, because it has its own role in security. Okay. So, so far we looked into various parameters or various trade-offs in the form of the cache design. And this slide is just a summary when you want to think about reducing misses. What should be your design parameters? What should be your line size, associativity, or cache size? Keeping complexity, the energy and power aspect, or the area aspect also, right? So depending on your goal, you may want to compromise on one of the trade-off and then try to improve the other, right? So something that I should emphasize when you are dealing with defining or quantifying the performance of a cache or cache hierarchy, usually you will find that hit rate and miss rate are kind of commonly used terms. But they are actually not representative terms. Why? Because hit rate and miss rates are just like ratios. They just talk about how many requests my cache get and then how many hits or misses my cache provides. And ratios can be confusing. They may lead to incorrect conclusions. Instead, a better metric is called misses per kilo instructions, which is correlating with your actual program. Your program has instructions. So if you are getting more misses for 1,000 instructions, that means your cache is actually not helping you, right? Compared to miss rate, this is a better metric. And another typical metric that is widely used is the notion of average memory access time, right? Whenever you are searching something at the cache level, that takes some time. The comparison, tag comparison, and then the extraction of index bits, that's called the hit time. If you're actually missing the cache, depending on the probability or depending on what fraction of accesses you're missing, there will be a penalty, right? And the penalty will be again depends on like which particular cache level or DRAM is actually responding, right? Ideally, we should have hit time low, miss rate low, and miss penalty low, right? So if you get a cache with miss rate of 0.00%, then that's it. There is no need of designing multi-level cache hierarchy, and there is no need to go for DRAM. Okay. So there are plenty of optimizations that are possible. I won't go into the detail because this is actually a workshop on security. But if you're interested, you can refer any standard textbook on architecture or go to my course website. Again, why it is important in the context of security, because whatever ideas are proposed in the past, they're actually, they're opening new doors in the form of microarchitecture security. Okay. I'll pause again, and then we are kind of in the last phase of finishing the basics, and then we'll jump into the security part. Any questions at the moment?
Sivaredi Vanga has raised hand.
Okay. So there is a question from Biman. In the equation of average memory access time, why hit rate is not there? Yeah, so hit rate is kind of subsumed. Irrespective of hit or miss, you will actually go to cache and try to find out, right? So the hit time is irrespective of your hit rate and miss rate, right? If you get a hit, it's good. If you get a miss, anyway you have to compare, right? So the hit time is actually the comparison time, the tag comparison and the index extraction.
Sir, can I ask a question?
Sure.
Sir, I am Puneet Namdev and I am lecturer and IoT practitioner. Sir, I want to know these too much detail on memory and architecture, but how this is relevant to study the hardware security of any system, sir, which we are designing. So these details are too much, sir, and deep. How we can relate it with our hardware security which we are designing and which we are operating?
Okay, so this is microarchitecture security, bit subtle. So you can't correlate all this with the hardware security that, let's say, Neeraj talked about in the previous session, right? So here I'm kind of focusing only on the memory hierarchy aspect or the processor out of order processor aspect, right? So it may happen that the hardware device that you are talking about, they don't have the caches or they are not operating on out of order processor, right? So mostly the security aspects that I'll be talking about, that they will be related to some of the modern servers or desktop or laptops that you are using, and not all kinds of tiny hardware device that you may be using in your day-to-day life.
But sir, I think memory is an important element in each system design. So
yeah, but
can
there is
you
a certain point. Actually, memory is not part of
put some
microarchitecture.
highlight on what memory aspect we are needed to be make more safe and secure environment for our IoT practices?
I got it. So if you look at the title of this session, right? So it's about microarchitecture, and memory is actually not under the purview of microarchitecture, right? So I think there are sessions tomorrow or day after tomorrow where there will be detailed discussion on memory, right?
Okay, sir. Thank you for
Okay,
giving
yeah.
such deep details, sir. Thank you so much.
Okay, thanks.
Sivaredi, you have a question? I see you have raised your hand. You can speak, or you can type your question in the chat box. Okay, no response from him.
Okay, so then maybe we can move on, or is there anyone? Okay, so then let's move on. So that was kind of a quick 10,000 feet view on caches and single core, but nowadays almost all the machines are multi-core. So it's really important to understand what happens to these caches or the cache hierarchy when you are talking about multi-core systems. And then multi-cores are kind of everywhere. Even your mobile phone is nowadays like 4-core, 8-core system, right? So at a higher level, nothing significantly different. But what you will find, which is kind of a concern from the security point of view, is you will find a shared structure now. So here I'm showing a 4-core system where there are private caches. They are running 4 different processes or applications. But finally, they are sharing a cache which is let's say bigger compared to L1 and L2, and that can be accessed by any cache. Okay. So previously we used to have a shared DRAM where if you are actually pointing the same address, then multiple processes can actually go and access a particular address in DRAM. Now, if 2 different processes are, even if they are not accessing the same address, if they are mapped to the same set, now they can create problem, right? Because if they create conflicts at a particular set level, that can lead to some of the key security properties that Neeraj was talking about in the morning. Okay. So in the multi-core system, you should start asking questions, right? Why have a shared cache and private cache? Why not have just one cache, right? Let's say if you have 100 cores, let's connect all the 100 cores and then have a cache, right? Well, the problem is the bandwidth, right? So this is similar to the example that I have been using from last few years. Imagine, 100 monkeys want to eat one banana. That will be the similar situation here, right? Instead, if you have private and shared cache, the beauty of this intuitive design is not all the applications will demand huge amount of caches. Let's say if you're running a small program, it may fit into your cache, right? And at the same time, the last level cache can be used by other processes, right? But if you make it private, then it's kind of completely wasted of the resources, right? So basically, you will find applications in the form of cache fitting, core cache fitting, meaning L1 and L2, or they're kind of tracing the LLC. Again, I'm using this term because I'll be using it again when I start talking about the security. These are all important from the security point of view. And another crucial subtle point, I won't go into the detail. Even though we have a last level cache which is shared among all the cores, since it's big, it may create bandwidth issues and it may create bandwidth contention. So they are actually sliced. What I meant by a slice is 8 MB cache will be sliced into 4 2 MB slices, so that multiple cores can actually start accessing. But remember, the slices are shared by all the cores. So core 0 can actually access slice 3, core 3 can access slice 0. Okay, but just to provide concurrency among all the processes, so that you can provide better bandwidth, this notion of slicing is actually used. Another thing, again, from the cache hierarchy point of view, and then which has its own implication in the security world, is when you design a multi-level cache hierarchy, what are the properties or what are the semantics that all the levels of caches should respect, right? So it's known as the inclusive property, the first of its kind, where whenever you respond something from the memory, you kind of put the data in the last level cache and also in the L1 and L2. And whenever you evict something or replace something from LLC, you also make sure that that particular block is not present in L1 and L2. Okay. Why? Because the definition says the last level cache is inclusive of L1 and L2. That means whatever data you have in L1 and L2 should also be there in LLC. So this was used for another reason that I won't get into the detail, but you will still find some of the commercial machines which are using inclusive caches. The other kind of property that you can find across cache hierarchy is non-inclusive, where there is no binding between cache hierarchies, the different levels of cache in a cache hierarchy. Okay, so you get a response from memory, you put it in first LLC, then L2. If you evict something from LLC, no need to inform the private cache because there is no inclusivity. The other extreme is called the exclusive cache hierarchy, where you actually don't put the data in last level cache. On a miss, or when you are responding from the memory, you directly put it in the private cache, L1, L2. And only when you are evicting the data from L1 and L2 cache, then only you put it in the LLC. Okay. So I'll come back to this again and then show you that how this hierarchies or different kinds of hierarchies can play a big role in the design of secure cache hierarchies. Okay. So with that, I'll stop. We have kind of spent around 45 minutes or so. And then the next 1 hour, 15 minutes, I will talk about security. So before we jump into security, any questions that you have based on whatever we have covered from the beginning? So this is kind of a pause. Okay, so this is kind of a break from the basic microarchitecture and the transition into security.
Sir, good evening, sir.
Yeah, good evening. Yeah.
Sir, just a few minutes ago, you showed us that all different cores will be using their slices over here. Yes, sir. The slices of the cache memory. So there will be processes in the course which won't be needing much of those slices, and there will be processes which will be needing a lot of memory. So do we have a solution for those type of things right
Yeah,
now?
the solution is the last level shared cache. That's what I explained a few minutes before, right? If let's say core 3 doesn't demand huge amount of memory, then it may happen that it will get its data from L1, L2, its own L1, L2. There's no need to go for slice 3. And in fact, slice 3 can be used or utilized in a better way by the other 3 processes or other 3 cores. Right? So it's kind of a dynamic decision by definition itself. Right? The notion of slice shared LLC is giving you that leeway.
Okay, sir. Thank you, sir.
Okay, thanks. Any other questions before we jump into security? Okay, so if all good, so let's move on to security then. So you must have looked at Intel commercials where the commercial says Intel Insights, right? So, but now from last few years, especially from last 4 years, you will find various kind of funny commercials where microarchitectural attacks are embedded with the Intel commercial. Okay, so these are some of the famous attacks called Spectral, Meltdown, and others, right? Which I am showing here. So we'll actually go through some of these attacks and then why they happen, if they happen, and then how to mitigate them, right? So that will be the focus for next 1 hour 10 minutes. You will find tons of media articles starting 2018. Even before that, there were attacks, but from last few years, you will find new and new version of attacks coming almost every month, if not every week. Okay. So I think Neeraj has already talked about it, but let me just reiterate the notion of security from the microarchitecture perspective. So this is the famous CIA property, the confidentiality, integrity, and availability. Okay. So from the memory hierarchy or the cache hierarchy point of view, or from the microarchitecture point of view, confidentiality means that you should not see an address if you're not supposed to see it. Okay, and the integrity comes one step ahead, where it says, okay, if you're not supposed to see something, then you should not change something, right? So that's where the row hammer attack comes, right? Where the attacker tries to hammer a particular let's say DRAM address again and again, and then in the process change the content of the address, right? So that's actually violating the integrity property. And finally, the availability that I think you can correlate easily. It's like, let's say we have the last level shared cache, right? What if as an attacker, you start writing a program that thrashes the last level cache all the time, right? Then the last level cache won't be able to, respond to other cores because it will be completely busy satisfying the need of attacker, right? So this is the availability aspect of security. In this session, we will mostly talk about the confidentiality and maybe a bit of availability, but not integrity. So integrity will come maybe once we jump into DRAM. That will come maybe tomorrow or day after tomorrow. Okay. So before jumping into how caches can actually leak information or how any microarchitectural unit can leak information, let's take a simple code snippet and tries to understand, and then let's try to understand. Okay. So this is a famous algorithm which is known as the modular exponential. Okay. But instead of going into the crypto side, let me get into the architecture side of it. So let's assume that the attacker wants to get the value of E. So E is actually an array of zeros and ones, okay? And you are not allowed, or as a process, you can't see the value of E directly. That's the threat model, okay? But you know that this particular crypto algorithm has the following statements that I'm showing here, right? So if you observe carefully, what happens is you actually iterate over that particular exponent, which is of, let's say, few bits, let's say 64 bits, 128 bit, whatever, right? And depending on the content of a particular bit, you do some operation. For example, if the content of a particular bit is 1, then you do a multiply and a reduce operation. But if along with a bit of square and reduce, but if a particular bit is only 0, you don't do multiply and reduce, right? So if you kind of connect all the dots, you will know that a particular index in the encryption or the exponent is actually corresponding to 0 if it's not accessing these addresses. By the way, these are all addresses, right? Because eventually you will actually call some functions which are mapped into memory. They will be there in the caches also, right? So the goal of the attacker here is to get this particular exponent and then through microarchitecture. Okay, so let's see how it can be done. So as I have mentioned, latency is the main bottleneck, or the memory wall problem was the main bottleneck. That's why we came up with multi-level cache hierarchy. But this is actually the major contributor for these attacks. Now let's see how, right? So I talked about the notion of the square reduce or square reduce followed by multiply reduce. So what the attacker can do is it can write a small program, maximum 3 to 4 lines, and try to find out the time it takes to do a load or time it takes to access an address, right? And then it can actually find out or create a threshold. So here in the y-axis, I'm showing a threshold of, let's say, 100 cycles. And there are few accesses which are taking 300 cycles. So as you have already looked into the basics of caches, you can easily say that, okay, these are the accesses which are actually there in the cache. And the upper part of this plot is actually the accesses which are actually coming from the DRAM, right? Now, if you have this first level of information that, okay, these are the data from cache, now what you have to correlate is whether these addresses are corresponding to the square function, the reduce function, or square reduce multiply reduce function, right? So if you look at the x-axis, the attacker can easily kind of map the accesses and try to correlate, let's say, the SR as 0, the SRMR as 1, right? But the question that comes to our mind at this moment is how to make sure that these accesses are actually from the victim and not from someone else, okay? So that we will see later. But this is pretty high level 10,000 feet view of how can you extract information by looking at the latency differences. That's why it's called the timing channel. But the attacker is not doing anything but just probing the time it takes to load an address or access an address, right? So you can simply write a for loop accessing an array and observe the access time. And if you suddenly see, oh, there is a difference, that means it's there in the cache. But if you can also say that, okay, this was actually brought into the cache by a victim, then yeah, you will be able to extract the key, okay? So again, pretty high level toy example, how exactly you can write a code. So basically we are trying to exploit some form of control flow dependency, right? So if there is a secret bit 1, then the crypto algorithm was accessing some address. If not, it was not accessing that address, right? So the attacker, what it can do is it can actually use, let's say, some sophisticated instructions called CL flush. So the notion of CL flush is it will flush the data from the entire cache hierarchy, meaning it won't be there in the cache after the completion of that instruction, right? And then the attacker can start a timer, just use get time of the day. It will give you a cycle number. Then you access that address and again end the timer. So whenever you get a fast access time, and remember you have already flushed, that means you are not bringing the data. But still, if you are getting the data from your caches, which means low latency time, that means someone else has actually accessed it, right? And that is actually your victim. And you are actually trying to get the data that victim has accessed, okay? Or at least you are trying to observe the access patterns that victim has accessed, right? So the timing channels are actually divided into broadly two categories. One is called the side channel, and another one is covert channel. So in the side channel attack, at a high level, you can assume in a multi-core system there is a victim process and there is a spy process, and the spy process is writing code to understand the timing differences, and based on it, it's trying to understand what exactly victim is accessing. Okay. The reason behind calling it as a side channel, because it's actually not the intended channel of information leakage. The crypto algorithm was properly secured. There was no harm in that. Even the software was secure. But when it was executing in the processor with caches, then only this kind of unintended channel pops up, right? The variant of side channel is covert channel, where there is no attacker or victim. Instead, there are two attackers. And you can imagine like two malicious processes, let's say one spy and one other Trojan, they want to communicate with each other through caches or memory where they're actually not supposed to, right? Let's say from the OS perspective, virtual memory is on, everything is on, and they are kind of isolated. That's why there is this boundary that I'm showing. But through this cache hierarchy, they can actually communicate. Okay, they can create a covert channel depending on the latency difference. So for example, if this guy wants to communicate one, it will say that, okay, if you get a slow access time, that is one. If you get a long access time, it's 0. So this guy will just probe its cache. Whenever it gets a low access time, it means his friend has sent a 1, or his friend has sent a 0. Okay. So let's look into the details of these attacks. Anyway, these are at a pretty high level. We will be mostly talking about the last level cache attack, which is shared among multiple cores. And as I have already mentioned, it is successful because of the timing difference, the latency difference. Getting the data from DRAM is much more costly compared to getting the data from the last level cache. So there are variants of attacks, and mostly broadly they can be classified into two kinds of attack. One is the CL flush based attack, where the attacker uses an instruction called CL flush. And there are eviction based attacks. So remember the replacement policy that I talked about a few minutes before, the Lru policy. So here the attacker will actually access more and more cache line in a particular set, so that the victim's cache line will be evicted or replaced, right? So you can simply think about accessing an array again and again, and because of the Lru policy, all the other data will be kicked out, right? So that's the base for eviction based attack. So let's start with the first attack, and then just to make the discussion much more at a higher level, the threat model that we can assume for next 1 hour is, if an attacker is able to find out a set number, right, that the victim has accessed, then we can consider it as a successful attack. Okay, so forget about the exact line number. Even if we can say that, okay, the victim has accessed set number 102, then that itself is a successful attack, because then you can actually do a bit of post-mortem analysis, a bit of brute force approach to finally get into the address of interest. Okay, I'll pause here before we jump in, because this is the first part of the security. So yeah, I'll be happy to take questions now.
Yeah. Hi, Professor Biswa. This is Prathamesh.
Yeah, hi, Prathamesh.
Yeah, so I had one question that all these attacks you were mentioning, all these attacks are timing based attacks, or are there any other scope as well for shared caches?
Yeah. So that's a good question. So in this session, I won't be talking about other kinds of attacks, but timing is one of the most widely used tool for attacking. But you can also come up with access based attack, where you don't observe the timing. Instead, you just try to observe some kind of accesses or access patterns. Okay, and then you're kind of aware of a predefined access pattern. So if something goes wrong in that access pattern, then you can conclude that okay, something is not right or something is leaky. There are other kinds of attacks like occupancy based attacks, where the attacker can just thrash the LLC, and the goal of the attacker is to understand what is the working set of the victim. Okay, the attacker is not interested in finding out a particular encryption key. The attacker is trying to find out whether the victim is using few KBs or 100 KBs or 100 MBs. So if you trash the entire cache and then sit idle, then the victim will come and then access few blocks. After that, you trash again. So in that case, if you start getting hits, forget about timing. Okay, even if you get high latency, it doesn't matter. But if you get more and more hits, so then finally you can conclude that okay, maybe the victim was actually using a small working set application, right? So there are many variants, but timing is one of the tool or the primary tool to get the information leakage.
Okay, thank you.
Thanks. Any more questions? Okay, if not, we can get started. Okay, so let's start with the flush reload attack. So one of the fundamental difference between flush reload and the other eviction-based attack is in the flush reload attack, the minimum requirement is both the attacker and victim, they are actually sharing a particular address space. What I meant by that, so take a simple AES crypto library. Let's say that is used by both attacker and victim, right? So that means that particular library is mapped to the address space of both the processes, both the attacker and victim, right? And even if the attacker is not allowed to access or not allowed to observe what exactly the victim is doing, but thanks to our last level cache, we'll be able to do it. So let's see how it can happen. So take an example of a library. Okay, it's a shared library that is used by both attacker and victim. So the attacker actually first flushes a particular cache block or a cache line, and then the victim accesses it, which means it reloads the block from the DRAM, and then the attacker tries to reload it. Okay, while reloading, if the attacker gets a hit, that means victim has accessed this particular block, and the attacker can actually infer that this is the address which victim is accessing, right? So remember, because attacker has actually flushed the block, so there is no way that attacker should get a hit. If it is getting a hit, that means someone else has actually brought it into the cache. Okay. A variant of flush and reload attack is flush and flush, where instead of reloading, you actually go for a flush operation again. So the idea is again similar. Both of them are actually sharing a particular library which is shared into their memory space. The first step is the attacker flushes the cache block. Second step is again same. The victim reloads the block. But in the third step, the attacker doesn't reload. Instead, it flushes, which means the attacker tries to flush the content of the cache into the memory. Okay, that's the notion of flush. But how does it help in getting the information, right? So to understand the subtle point, whenever there is a hit in the cache for a flush, then the flush instruction takes more time. Why? Because that means there is something present in the cache and the cache controller has to flush it to the DRAM. Okay, that's the semantics of CL flush. So if you are getting a CL flush miss, that means victim is not, or victim hasn't accessed that particular block. Okay. So to give you a detailed picture, so this is actually the latency distribution of some of the recent Intel machines. You can see the CL flush hit and miss timing differences in terms of cycles. So CL flush hit takes around, let's say, 110 cycles, but CL flush miss takes, let's say, less than that, right? On average, if you look at this plot, more than 75% of the time, right? That is the distribution. It's taking 110 cycles, right? So based on this, you can actually infer that whether the victim has actually accessed a particular address, right? Having said that, this attack is extremely noisy, though people have tried it, but it doesn't work in real machine with multiple processes. But the flush reload attack is much more resilient to system noise. Next, let's move on to a scenario where both the attacker and victim, they are not sharing anything. So the example that I was talking about the sharing of a crypto library or in the form of an AES library. Now let's assume both of them are actually not sharing anything. So that means you can't CL flush or you can't reload the same address because that is not mapped to both the processes. So instead, they are kind of two different isolated processes. Their address space is different. Their virtual address is also different. So can you still attack? Okay. And then the answer is yes. And the attacks are actually the eviction-based attack. One of the famous eviction-based attack is called prime and probe attack. So at a high level, what this attack does is the attacker will fill the entire last level cache. It's pretty easy to do it. Just write a for loop and make sure that you use a large array, which is larger than the last level cache. It will fill the entire last level cache with your own data. Now the victim comes. Remember the replacement policy? Victim will get a miss because the LLC was completely full with the attacker's data. Now victim will evict some block because the cache was full. Replacement policy will kick in. And depending on the victim's requirement, victim will start evicting few blocks. After few cycles of few interval, the attacker will come again. It will probe the cache, right? So probing meaning it will again try to access the same addresses, the array addresses that it has actually primed in the first place, right? So if it misses, that means victim has actually accessed a particular set, right? So at a high level, what attacker is doing is it's thrashing the cache and waiting. And if victim has access, that means some of the attacker's blocks were evicted. And then attacker is trying again to see whether it's getting misses by observing latency numbers. Okay. One of the crucial questions here is how does the attacker know which set number? Okay. So there are sophisticated algorithms which are designed to prune the entire LLC into few sets, which are known as the eviction sets. Okay. So instead of thrashing the entire LLC, the attacker can actually, try to reverse engineer the index bits and other bits that we discussed an hour before, and make sure that those are the sets of interest, and it will start thrashing those sets, not the entire LLC. Okay. Having said that, all these attacks are not that easy to mount. Based on my personal experiences or my student and my experiences, it takes around months to successfully attack a cache and then successfully retrieve some keys. Okay, so one of the key or one of the pertinent parameter while attacking caches is the notion of waiting time. Okay, so here I am actually showing the time window where the attacker actually primes something, then waits, then probe. Then it may happen that during that time the victim doesn't come. The victim process is not running in the system, right? Then attacker won't be able to get anything. The ideal scenario for a successful attack is the victim should come when the attacker was waiting. That means the attacker was done with the prime phase. It's waiting for the victim to come, and then it will again go for the probe, right? And it may happen that the victim is actually coming in between the probe phase and in between the wait phase and the probe phase, right? Again, the final outcome will be noisy. Or it may happen that the attacker is coming multiple times during the wait phase, right? So depending on which application you want to attack, the weight parameter or the waiting times should be configured empirically, right? So typically, few thousand cycles is actually a good estimate for attacking some of the existing applications, but it's not it's not a rule, or it's not a fixed policy that you should actually only wait for 5,000 to 10,000 cycles. Okay. Remember the notion of inclusive, exclusive, and non-inclusive caches. Let's see how this can actually help an attacker, right? So remember the inclusive cache. In the inclusive cache, I said that the last level cache is a superset of L1, L2, which means the data that is present in attacker's L1, L2, the data that is present in victim's L1, L2 is also present in LLC. Okay. Now, the goal of the attacker is to make sure that the victim comes to LLC, right? Irrespective of its working set. So, in a small crypto application, or for a small application, the victim should actually get hits in the private cache, right? So victims should not come to last level cache. But because of inclusiveness, let's see what happens. Let's say the attacker thrashes the last level cache, right? And because it thrashes, obviously the victim's block will be evicted or replaced from the last level cache. When it is replaced, what happens is, just to maintain inclusivity, the cache controller will actually send a message to the victim's private cache saying, I have replaced your block from the last level cache. It's time for you to be kicked out from the L2, L1, whatever, right? So this term is known as the cross-core Beck invalidation or cross-core inclusion victim, right? So just because of inclusiveness, now the attacker can actually affect the victim's private caches, forget about shared cache. It can actually start evicting blocks in such a way that because of inclusive property, the victim's blocks from the private caches will be evicted. So now it becomes easy. Next time the victim comes, it has to come to LLC. There is no way it will get a hit in the L1. I hope it is clear. But from last few years, all the commercial machines, they have started jumping into non-inclusive caches, because inclusive caches are making this kind of attacks much more easier compared to other exclusive and non-inclusive attack. Right? I'll pause again before we jump in. Any questions so far on these three attacks? Okay. How can we go about implementing this timing-based attack on computer architecture simulator? As far as I know, hardware security researchers are using FPGAs. No, so you can actually implement these attacks on architectural simulators. It won't be a daunting task. Whatever processes or events that we are discussing, we have to just simulate the same thing. And then if you're going for any standard architectural simulator, you will find caches are already there, processors are already there. Now you have to just make sure that a particular semantics of attack is kind of simulated. Okay, what are the simulators and tools to study hardware security? Hardware security is again a broad term. I'm just talking about microarchitecture security. Okay, so be careful with that term. So there are many architectural simulators which are, you can call it execution-driven simulator or trace-based simulator. So you can go for Gem5, Sniper. There is this ChamSim, which is a trace-based simulator that I use, right? So just Google for architectural simulator and you will find many links. Okay, so there is another question. Does inclusiveness and exclusiveness have something to do with? No. So yeah, this is a very good question. So what Bhuman is asking is whether inclusiveness and exclusiveness has something to do with the write through and write back cache. No. It seems that they are related, but they are not. Okay, write through, write back are different policies.
Yeah, I have one question, Professor.
Sure.
Yeah, so you mentioned about this inclusiveness. So what will happen if we are trying to deal with inclusiveness? So there was this one paper this year, ZIV, Zero Invalidation Cache, in ISCA 2021, in which they are trying to randomization of LLC sets because of this invalidation. So how do that will affect?
Yeah. So the zero inclusion victim is actually not randomizing. What it is doing is, thanks for bringing up this paper. This paper, what it does is it makes sure that it doesn't create a cross-core bake invalidation. That's the contribution of the paper. Okay.
Yeah,
So
but are the changing of the mapping of sets, right? Because
it depends. Okay, so that's the implementation detail, like how exactly you will implement an inclusive cache, which can make sure that you are not creating cross-core bake invalidation, right? So you can actually go for remapping of blocks, or you can actually try to delay this invalidation to some of the blocks which are not present in some other course private caches, right? So these are all design choices, right? But at a high level, the goal is when you evict something, make sure that that's not there in the private cache,
yeah, yeah.
right?
Yeah, but we have to choose some eviction candidate. If all the blocks in that
Exactly.
set, yeah, okay.
Yeah. That's a difficult problem to solve, right? So whether you'll go for a random policy or you will actually go for something else, right? So it has its own trade-off.
Yeah, okay. Thank you.
Yeah. Thanks. Some more questions before we jump in? So far, the takeaway is there is a flush-based attack where both the attacker and victim are kind of sharing a page, or there is eviction-based attack where there is no assumption about attacker and victim, and you are kind of exploiting the replacement policy, because the replacement policy will kick out something, and then you are just scratching the cache. Okay, then. So let's talk about the practicality of these attacks, whether your bank accounts will be hacked through these attacks, right? Or are there any real heists that have been done through these cache attacks, right? Well, the answer is no. At this moment, the answer is no. But I'll give you a pretty simple reasoning why we should care about these attacks. Okay, and then the reasoning will be clear in maybe next 5 to 10 minutes. Okay, so I'm jumping into two attacks called Spectral and Meltdown. Okay, and they are again using cache as a side channel, as a timing channel. But the core of this attack is the out of order processor and then some other microarchitecture concepts. Okay, so let's understand this, and then we'll come back to the practicality. Okay, so if you are aware of Spectre, then it's good. If you are not, then it's even better. So let's see what exactly Spectre attack is. Okay, so let's look at this code snippet. Only 4 lines, pretty easy. So there's an array which is of size 3. There are 3 entries in the array, and let's assume that this is a code snippet which is part of victim. It can be part of OS code, maybe some system call or whatever. Okay, let's not get into that. But let's assume that this is part of some victim, and some core owning processes are actually providing an input to the victim, and the core owning process is actually an attacker in our case. Okay, so in this case, what I'm showing is if the attacker it's a variable which is provided by the attacker, the value is 4. If it is less than the size of this array, then go and access this particular array, which is my array. Okay, remember, my array is actually accessible by the attacker, but this Atal array is not accessible by the attacker. Okay, so Atal array, it's not mapped to the attacker's address space. It can't access directly. Okay, so through this attack, we will see how a process can actually access the content of another array which is not mapped to its own address space. Okay, so few more assumptions that can be easily established. Let's assume this particular query size of this particular array will actually go for a DRAM load. Why? If you just trash the cache, then you can actually be pretty certain that whoever access this particular address, it will actually go to DRAM, right? So that means anything that is concerning to the Atal array will actually go to DRAM load. You can actually thrash it, right? Think about the prime probe attack that I talked about, right? Now the core of this attack, what happens exactly is when the code executes this particular statement, the if statement, in the microarchitecture, there is a structure called branch predictor. Okay. So the notion of branch is whenever you are jumping or you are kind of, going towards some other part of the program, you need a branch predictor. So simple examples are your if else statement, some loop conditions, and blah, 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 right? So what the attacker can do is it can actually mistrain the branch predictor so that the branch predictor will return true here. Okay, but it should actually true false, right? Because the value 4 is less than size of util array, which is 3, right? It's actually a false statement. But the predictor will actually say, no, it's true. I have seen this before and it's true, right? So just to give you a high-level overview, if you are not aware of branch predictor, so this is a structure which is sitting in the processor pipeline, and the goal of this particular structure is to give information about whether a particular branch will be taken or not taken, right? Whether the condition will be true or not. And if it is true, where exactly it should jump. The program should jump to which part of the program, right? So typical examples of branch or jump is your loop, switch statement, or if else, right? Now, having said that, let's come back to the attack, right? So the attacker has mistrained it. How? The attacker has actually written code in which this particular part was always true, right? So the branch predictor, it has trained, so you can assume it's actually using a learning algorithm. It has trained itself saying, okay, every time I see this particular if condition, it's always true, right? But attacker has actually fooled this particular branch predictor. Now what happened, the processor is actually executing something that it should not execute. That's why it's called the wrong path execution. Okay. Remember, this condition is actually false, but because the branch predictor says no, it's true, the processor will actually start accessing this particular statement, to start executing this particular statement, right? And depending on the time it takes to finally resolve this particular wrong path delay, you can actually get the data for this particular array, right? So what I meant is the processor is actually on the wrong path, but eventually there is a mechanism through which the processor will be informed that no, whatever you are doing is actually wrong. So it's time to undo whatever you have done. Okay. But that may take around 200 cycles because, as I have said, this util array is not there in your cache, so it's going to DRAM. So that means this particular condition will be, it may take around 200 cycles, right? But in the meantime, the processor has actually moved forward. It has accessed this particular my array, right? And so that means the util array 4 is already there in the private caches or in all the caches, L1, L2, L3. Because the processor has moved ahead and it has started accessing these addresses, even though it was not supposed to, right? So the addresses are also in the cache. Now you can what you can do is you can just go for the existing attacks that we have discussed so far, right? The flush reload and prime probe cache attacks, right? So you can actually try it out on these addresses, and finally you will be able to get the data. So let me just show you that in a few slides. So finally, the processor realized that it's a mistake, and then it's to undo whatever instructions that it has executed, but the data is already there in the cache. Okay. So let's see how the attacker can get the data. Now the attacker will actually just do a reload of its own array, which is the my array, right? So it can actually write a for loop where it will go through my array 0, 1, 2, 3, 4, 5 like that. Okay, and it will observe the timing differences. So let's say for my array 0, it gets 16 nanosecond. That means it's not there in the cache. But suddenly for my array 1024, it gets a 5 nanosecond, which means my array 1024 will actually lead to a value 2 here, right? That means 2 into 512 will give you 1024, which is nothing but the content of util array, right? So which means the value of util array with index 4 was actually 2, right? So this is actually next level of information leakage. There we are actually trying to observe the timing, and then we are trying to get the key by doing a postmortem. But now you'll be able to get the data directly, right? There is another variant. I won't go into the detail, which is called the meltdown. As I mentioned in the earlier slides, so this is an attack which happened because of the outer border processor. The processor looks at these two statements and see that there is no dependency. So it says that, okay, it doesn't matter whether I execute the first instruction first or the third instruction first. Okay. But if you look at the first statement is actually raising an exception, that means something is wrong. But the processor won't care about that. It will start executing something which is part of kernel accesses, let's say, which is, let's say, the entire OS address space, right? Now, again, go back to the previous slide where all the accesses can be in the cache, and then the attacker can actually just do a prime probe attack to get the data or dump the entire OS address space, right? So this is called the meltdown attack, right? So you can actually ask question, right? So this is a kernel address, kernel data structure. It should result a page fault, right? But again, the page fault will be handled at the time when the instruction is actually about to complete. Okay, so it won't be handled immediately. So that's why these attacks happen. That's kind of a curse of out of order execution. Okay, I'll pause here if there are any questions on Spectral and Meltdown. If not, we'll jump into the last part. Any questions on Spectral and Meltdown?
Yeah, so the thrashing of the application is always necessary. Is that correct? That whenever LLC thrashing?
Kind of. At a high level, yes, but there are more sophisticated techniques where you can actually thrash a few portion of LLC and not the entire LLC.
Because there is always an attacker and victim, but in real system there will always be some neutral processes. So if thrashing is not done, then it's difficult to identify. Am I correct in this way?
Yeah, you are correct. Yeah, it will be noisy.
Okay. Noisy, yeah. Okay. Yeah, thank you.
Okay, so any other questions? If not, we'll move on. Okay, so before moving on, I should actually talk about the practicality that we talked about initially, right? The practicality is if the community would have solved the plus reload and prime probe attack, then Spectral Meltdown would not have happened. Yeah, there are various variants of Spectral Meltdown, but one of the primary variant was through caches. So if the community would have solved the cache attacks, then the Spectral Meltdown would not have come in 2018. Okay. So with that, I will jump into a few quick ideas in terms of mitigations, like what can be done to mitigate this kind of attacks, and then we'll conclude and take more questions. Okay. So mostly the mitigations are divided into two techniques called cache randomization or cache partitioning. So if I have to summarize the last level cache, we discussed that there is an index bit, there is a tag bit, there is a deterministic mapping between address and set number and line number. The last level cache is shared among multiple applications, and there is a latency difference which is distinguishable, right? These are the three key properties. So now we have to break them, right? So the first property is there is a one-to-one mapping between an address and a set number, right? So how can you break it? You go for a non-deterministic, randomized cache where given an index bit, it may happen that it will, map to random locations. So which means A0, which is supposed to map to set 2, it may map to set 4, right? And you can do it repeatedly. Otherwise, if you just do it once, the attacker can actually make an attack, if not now, tomorrow, right? So pretty obvious idea at a high level. So you need an encryption engine, which is sitting beside your cache, which is taking the index bits, and every time it's kind of using a key to decide what will be the set number, right? And the key is changed periodically. Otherwise, this will again become a conventional deterministic cache, right? So with that, I'll kind of jump into other ideas. So this is a high-level randomized cache idea, okay? But the limitations of randomized caches, they don't guarantee full security. The applications are still contending for the same shared resource. The LLC is still shared by both attacker and victim. It all depends, finally whether the attacker can get the data or get some data eventually, right? It's just a matter of time. So the other way of mitigating these attacks is called cache partitioning, where instead of sharing the last level cache, you kind of partition it, right? And then you can actually partition it dynamically depending on the application requirement. So there are three different ways through which you can partition your cache. The first one is called the page coloring. It's more subtle, but let's try to understand it. What happens is you have the indexing function which gives you the set number. But through page coloring, what will happen is each process will have fixed amount of sets which are completely exclusive, which means core 1 can't access a set which is mapped to core 0. Okay, and how this mapping is provided? Well, this is provided through a pretty conventional idea called page coloring. So if we take the example of the address splitting that we had discussed before, and if we talk about a OS page size of 4 KB, what will happen is a 4 KB page will actually take 12 bits, right, from the address, from the lower LSB. And assuming the block sizes or line size is 64 bytes, and there are, let's say, 2048 sets, you will actually have 5 bits to play with, which is still part of, or they are contributing to the LLC index. Okay. Now, what you can do is, or the OS can do is, it can actually create 32 regions. Each region is of size 64 KB, right? So eventually what will happen? So each set will be assigned to a color. And basically it's saying my LLC is now collection of 32 different colors, which are mapped to 32 different processes. Okay. So in this way, there is no conflicts. There is no notion of replacement policy. Nothing will come, right? They are completely isolated. So I will share this slide so that you can go through it later. One of the limitations of this particular approach is when you are allocating your last level cache space, you have to allocate proportional space in the DRAM, because we are actually using page coloring as a way to isolate LLC, right? So if your application is demanding less memory but more cache, or more memory but less cache, then this particular approach is not that useful, right? So this is a limitation. The performance, the application execution time will actually go up. The other approach is called the way partitioning. Pretty simple, as I have talked about, two-way set associative cache or k-way set associative cache. You can actually come up with mechanisms where different processes are actually restricted to few ways, not all the ways. That's the idea. That's all, right? If there is a spy and victim, so this way partitioning will say, okay, if my cache has 4 ways, I will give 2 ways to spy, 2 ways to victim. Remember, the replacement policy will be limited to the ways of the spy itself. The spy can't evict something from the victim's ways. Okay. Again, you can go through it in detail later, but one of the limitations of this particular idea is the number of regions, the isolations, that boundaries that you are creating is limited by the number of ways, right? In modern processors, they have like 16-way last level cache. So that means at a given point of time, you can actually have 16 different isolation boundary. Okay, not more than that. Finally, there is something called set partitioning, where it's different from way partitioning. It's similar to the page coloring, but instead of using page coloring as a mechanism to provide isolation, you can come up with your own mapping function, and that mapping function can actually decide which are the sets that a particular application will use, right? So you can decide that application 1 will use cluster 1 and cluster 4, where each cluster is defined as a collection of sets. Okay. Again, you need a bit of OS support, or at a higher level, what Neeraj was talking about, some notion of root of trust at the beginning, which can actually provide this kind of feature. Okay. So similar concerns are there even with set partitioning. How many clusters to allocate a particular application? How will you decide? These are kind of design choices, right? And then whenever you you are done with a particular application, then you have to flush that particular cluster, because now that won't be useful unless you flush it, because you can't allocate that cluster to someone else, right? So these are kind of high-level gas mitigation techniques that can mitigate the prime probe or flush load kind of attacks. The kind of attacks that we talked just before discussing mitigation, the spectral and meltdown, they work because of something called a transient behavior of the processor or a speculative behavior of a processor, where the processor knows it has made a mistake, but it resolves it later, right? And during that time, in the spectral attack, the attacker actually brought the data into the caches, right? So one of the proposals is, you get the data into a new cache level called, let's say, L0, and L0 is kind of speculative. So whenever you are actually in the speculative window, where, let's say, after each if condition, if you are bringing something, you bring only to this particular caches, not to all the caches that are there in the cache hierarchy, right? So, and then eventually, once you are clear that, okay, that particular if condition is true or false, then you can actually move the data back into the next of the cache hierarchy, right? So that's the idea. So it's a one more level of cache hierarchy, which can store only the speculative blocks, and then the rest of the cache hierarchy is completely unaffected, right? So in this way, you will be able to mitigate the attacks like Spectral and Meltdown. Okay, so I won't go into the details because that was the top level view. So you can actually go through the slides later to get a more detailed view, right? And then another thing that is crucial for all this kind of design is whenever there is a context switch, you are moving from one process to another, you have to make sure that all these caches are actually invalidated. Otherwise, again, the data will be there in the cache and someone can actually attack, right? So with that, I will kind of pause, and we are actually jumping into the last few slides. Any questions?
So there is one question by Dr. Biman.
Yeah, can hashing help? Yes, sure. So hashing is one form of providing a different indexing function which can provide randomization, but the hashing function should be non-deterministic. It should not be deterministic. Okay, so maybe let me quickly go through the last few slides, and then we can start taking questions. So the overall summary of this particular session is, these attacks are actually not that serious when you talk about all the other attacks that you see in the news. But as I have mentioned, right, if you would have solved the cache attacks, spectral meltdown would not have come, right? So there are actually two sides of this microarchitecture security research. One is the offensive side, where you kind of try to propose or come up with new attacks and try to make the attacks more real, more vulnerable. And the defensive side is, can you design secure microarchitecture without compromising, let's say, energy, performance, or whatever, right? So these are the typical security questions. Security-related research questions that you will find in research community. So I have listed some of the top forums for reading papers, research papers in the field of microarchitecture security. Go and have a look if you are interested. So with that, I will stop, and I would like to wish you a new year, which is coming in next few hours. So thanks, everyone. I'll be able to take questions now, maybe for next 15 minutes.
Yeah, hi sir. So when we talk about this randomizations of caches to avoid these attacks, so what will happen to all the sophisticated replacement policies like Hawkeye and all the others, which need to store all the previous information? So that is now again corrupted, right? So
It's not corrupted. It's just that you need to have one more indirection, one more structure which can actually tell you that, okay, these are the reuse information of those blocks, right?
yeah, correct, right.
Right.
But the complexity will be much more higher.
Obviously, yeah, microarchitecture is all about playing with trade-offs,
Yeah,
right?
yeah.
So the recent, some of the ideas that have come, they say that RRIP policies, they kind of fare well, maximum 2% degradation on average, right? So it's on average, if it is 2%, it's okay. It's not a big deal,
Mm-hmm.
right?
Yeah. Thank you.
Yeah, yeah. Maybe I'll stop sharing my screen. Yeah, we can continue taking questions. I think last few slides I finished a bit faster, but I just gave the high level overview that was kind of needed to understand. Later on, you can go and look into the details.
Any more questions for Dr. Biswa?
Instead of questions, I'm just saying thank you. So maybe it's better to get questions instead of thank you. We still have 15 minutes to engage, debate, discuss.
That's okay, I guess. And regarding you, for the last few slides, the comment you made, I think that is okay because this is still the basic FDP, right?
Yeah.
Right.
I
It will
didn't
be
want to
good.
go into the subtle
Yeah, yeah.
issues. Right? So, yeah.
Yes. So I think the main intention is the participants should appreciate the need for such designs. That's all.
Yeah. Yeah, but feel free if you get more queries later, feel free to email me.
Yeah, yeah.
Yes. The feedback form is specifically for that. I know. Even if you don't have any question at this moment, use the Google form. I have made it editable. You can even you can submit multiple responses, right? Use that, and we will be directing the questions to the respective speakers, and we'll collect the
Okay.
responses and share it back to you. Okay. Yeah, and it feels good if you have given feedback apart from the questions also, because the speakers would work on it, and then they will be
Sure.
even they'll appreciate for sure. Yeah.
Yeah, Professor, can you give us a line of sight, like what would be the future direction if someone wants to pursue a research career in this area?
Wow. This is a hot topic, to be honest. But similar to other hot topics, there is a risk involved, right? It's kind of a cat and mouse game. Every few months,
Mm-hmm.
you will find there's a new idea, there's a new mitigation, there's a new attack. If your bandwidth supports that kind of cat and mouse race, then yeah, why not?
Yeah.
Like personally, I'm kind of struggling. Some of the ideas that I wanted to kind of communicate or I wanted to submit, they are already there on the market. So
Okay, so it's also race against time then.
yeah, exactly. It's a timing challenge attack, right? So
Yeah.
but having said that, I should not demotivate you, right? So see, all these proposals, they are still in the early days. Okay, so this line of research is not matured enough like other microarchitectural ideas, right? So you take it in that way, right? Or maybe you should try to solve this problem in a more fundamental way instead of randomizing somewhere here, maybe partitioning here and there, right? Is there a better
Mm-hmm.
way of doing it, right?
Yeah.
Yeah. So there are so many knobs that you can play with. You can talk about energy, you can talk about fairness, quality of service, performance, and security, right?
Right. Yeah.
Yeah. So I gave you 5 PhD problems, so that's I'm working on.
Yeah. Yeah, because you also mentioned about partitioning and also automatically fairness kicks in and then
Obviously, yeah.
a lot
So
of things. Yeah. 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 Thank you. Really appreciate. Very nice session.
Thanks.
Okay, so to all the participants, we have already updated the FDP webpage with the recordings of the first and second sessions, and the recording of this session will also be updated in the next couple of hours. So you can refer to them whenever you want. Yeah. Okay, if there are no queries, probably we can call it a day.
Here I have one question here.
Sure.
Yes, go ahead.
Who is
So,
this? Chandram, is it?
manufacturers like Renesas and the Infineon have few processors with not processor microcontrollers with HSM. So my question is it possible to replace this HSM with the software-based solutions because this increases the cost?
What is HSM? I'm not aware of it.
Hardware security model, they have the separate chip on along with the
Okay.
microcontroller.
No, so if you provide it through software, right? Again, whatever we have been discussing from last two sessions, right?
Mm-hmm.
To access those structures. So when you say software, meaning there is a software data structures, right?
Yeah.
That will be mapped into memory. Then again, all these attacks will come into picture. Yeah, obviously, if it is a microcontroller, there won't be caches, right? But even simple memory-based attacks can be performed, right? So that's kind of a trade-off. That's kind of a dilemma whether to put it in software or put it in hardware, right?
Mm-hmm. So do you wanted to say that with hardware-based solutions, we will get more security than these software-based solutions?
It's tricky. I should not say yes all the time. It depends because if the solution itself can be compromised, then again it's creating a new, new attack vector that you can exploit on, right?
Okay. Thank you, sir. Thanks.
Thanks.
Sir, I have one doubt, sir.
Sure.
Sir, you spoke about filter cache, sir. So, what are the techniques in implementing that filter cache?
No, that filter cache is pretty simple. It says that whenever the processor is actually not sure whether it is actually executing instructions which should be executed, you
Yes,
can
sir.
actually have a small cache to store the data during that part of the execution.
Okay. So, we can't implement any constraint or condition on that filter cache.
No, the condition is you should only store data in that cache during the speculative period, when the processor is not sure whether it is doing right or wrong.
Okay, sir. Thank you.
Okay.
Yes, thank you, sir.
Still have 8 minutes.
I guess we can call it a day if
Sure.
no questions. Yeah.
Okay, thanks everyone.
Yeah, and from all the participants' behalf and the coordinators' behalf, I like to say thank you very much for giving your time and interacting with
Hello,
all of us.
Kalyan. Hello, Dr. Vishwa. This is Shirshendu
Yes.
here.
Hey, hi, Sisandhu. Long
Yes.
time.
Sorry, I could not attend the complete session because there was some. I'm busy with some personal work, not at all academic. So, but I listened the first last 40 minutes I was present. So it was a very nice talk.
Okay, thanks.
Thank you very much. Thank you very much.
Yeah, I have got so many thanks. Maybe I'll just broadcast one thanks and get it done. Yeah, it was nice talking to everyone. Actually, I got really good questions, and hopefully it will be helpful. Okay then.
Okay. Yeah.
Bye.
Okay.
Bye.
Thank you, Hussein. And to all the participants, we'll meet tomorrow at 10 o'clock. We'll use the same meeting link, and the feedback link is also same. Yeah. Ankita, the feedback link is here. Right. And like I said, the recorded sessions are already been linked to the FDP webpage. Please have a look, and if you have any questions, put it in the shared Google form. I'm going to stop my recording now.